We live in 4 dimensions. 3 of them are space, because we can move up, right, or forward. The 4th dimension is time. When we combine all 4 dimensions, we get spacetime as a single entity. Where there is space, there is time, and the two are inseparable. General relativity says that when there is mass, it bends the fabric of spacetime. Imagine a person falling off a cliff. He would accelerate toward the center of the Earth due to gravity. But Einstein said that gravity is an illusion. Instead of the person falling toward the Earth, he wants us to imagine the Earth accelerating upward. In this way, an accelerating reference frame is the same as a reference frame in a gravitational field, at least locally. This is the equivalence principle. In the global frame, things become a bit more complicated. Imagine a map. To travel from point A to point B, the shortest path is a straight line. However, if we travel from point A to point B on a globe, the shortest path is no longer straight but curved. This shortest path is called a geodesic. If 2 people travel from their points to the top of the globe, their horizontal distance will get closer, even though, to them, they are moving in a straight line. The change in horizontal separation is purely a result of the geometry of geodesics. This idea applies to gravity as well. Objects naturally follow the straightest possible path in spacetime. When an object is near a massive body, like a black hole where spacetime is curved, it still follows that straightest path, only now within curved spacetime. This bending of paths is what we experience as gravity. Gravity is not an invisible force acting at a distance, but rather the result of curved spacetime, where everything tends to move along what feels like a straight line. In general relativity, it's not just space that gets curved by mass, time gets warped too. Near a very massive object, like a black hole, spacetime is curved so extremely that time itself runs slower compared to faraway regions. Imagine spacetime as a grid where the lines are spaced evenly, meaning clock ticks normally. But near a massive body like a black hole, those grid lines get stretched and distorted, especially in the time direction. This means anyone near such a massive body will age slower compared to a person on Earth. This is gravitational time dilation. When a light ray is emitted from a planet close to a black hole, a person on that planet measures the light to have a normal, high frequency, because their clock is running slowly due to the strong gravitational field. However, when that same light is observed from Earth, it appears redshifted. As the light escapes the gravitational well, it seems to lose energy, and since a photon's energy is proportional to its frequency, the measured frequency decreases. Because frequency and time period are inversely related, this decrease in frequency corresponds to an increase in the time period. This gravitational redshift occurs not because light slows down, but because time flows at different rates in regions of different spacetime curvature. This is one of the pieces of evidence that proves gravitational time dilation.